Hey everyone, and welcome to Blockchain Village. So in our talk, we will be covering about sandwich attacks, and we'll cover how we can prevent them with recurrent and recursive zero knowledge proofs. So starting with the agenda. So this is how it looks like for our talk. So giving you a quick speaker's introduction. Meet Mr. Gokul Alex, my partner for this talk. He's a cryptographer and cryptologist. He's a blockchain security architect, researcher on DDoS attacks. He has co-founded many projects, organizations. So popular of them are Gigamesh Garages, Semi-Out Systems, and Quantum Kicksort. He's also advisor at Red Team Hacker Academy and Red Team Cybersecurity Labs. If you want to meet him, you can visit his Twitter account, Twitter handle at GokulGaze. Next is me. My name is Tejas Surastogi. So I'm a penetration tester, a blockchain security researcher, currently a smart contract auditor at Cool Audits. I've also founded a RazorSec, which is an open source community of security researchers who come together and discuss on various security topics and help everyone to learn and grow. I'm also a creator at Cypher Shastra, which is a CDF platform where anyone and everyone can come and practice some smart contract challenges and also some cryptography exploitation challenges as well, might be in future. I'm also a malware analyst and adversarial ML researcher. If you want to connect with me, you can visit my Twitter handle at RazorTweet. So starting our presentation, let's take a quick refresher over some topics, starting with front-running attacks. So, what is a front-running attack? So front-running attack is something when an adversary having the knowledge of queued transactions places this transaction and which gets executed prior to a genuine transaction, thus impacting it. So how does this happen? So it happens because by tricking the transaction selection process. So as we know that blockchain is a public decentralized ledger, meaning all the data flowing in the network is publicly accessible. So when a transaction is signed and submitted onto the network, it is broadcasted into the entire network. So every node gets the information about it, and they all get stored into the mempool or memory pool. And firstly, they are marked as pending because there are a lot of other transactions flowing into the network. So a transaction just entered into the network will take some time and will be first stored into the map pool and will be picked up by a miner. So miners pick up the transaction to add it to a block, and they are incentivized for the block creation. But here comes an important factor, which is the gas price. Now the miners typically pick and order the transactions in descending order of the gas prices, which are associated with the transactions. So they do that to extract as much profit as possible from the block creation. So here you can see a visual representation of that. There are multiple transactions like T1, T2, T3 and T4. All of them have different gas fees associated with them. They will all go to a mempool, and miner will pick up T4 first because it has the highest gas fees associated with it, and following with the T3, T2, and then the lowest one, which is the T1. So this means that typically transactions are ordered on the basis of gas price and not as first come first serve basis, right? So the attacker can take advantage of it and send a transaction with higher gas fees than the victim transaction. So what will be our result for that? The result will be attacker's transaction will be picked up first, impacting the victim. So there are multiple variants or versions of front-running attack. Some of them are displacement attack. So as the name says, displacement. So it's when an adversary displaces the victim's transaction with its own and with the same values, which leaves the victim's transaction with no meaningful or effect, or in some cases they are completely orphaned. Example can be like consider a smart contract which accepts a secret number and gives the lottery to the user, whoever calls it first. Now the transactions after it will either be discarded or won't be making any money. So a genuine user, like the scenario, so a genuine user finds a secret number and submits the transaction. An adversary gets the info of this pending transaction from the mempool. It places this transaction with the same secret number but with a higher gas fee. So as a result, it gets picked up by the miner first and adversary wins the lottery, which leaves the genuine transaction meaningless. So another example can be, which is a popular one, as domain name registration. So imagine like a victim or user trying to register a particular domain. So an adversary sees this pending transaction with the registration request of that particular domain. The adversary can front run and buy the domain prior to the victim and can sell it afterwards with a higher price. So this is something called a displacement attack. Moving on to, there's an insertion attack. Insertion is where adversary places two transactions before and after the victim transaction, thus making a sandwich by inserting the victim transaction in between of its two transactions. Hence, sandwich attack can be thought of a kind of insertion attack. So we'll come to it later, as this is the main aim of our talk. So next is the suppression attack. Again, this is a popular attack. So here the sole purpose of this attack is to delay the victim's transaction. How does they do that? Like by filling the block gas limit, so that they can delay the victim's transaction for a certain amount of time. So when this happens, after that the victim's transaction again becomes meaningless, or it doesn't matter much, because as the adversary has already achieved its purpose now. So it can be thought of kind of a denial of service for the users, as adversaries want to maximize their profit per block. So this is also called as a block stuffing. So here our main focus is on the insertion attack. So insertion attack or a sandwich attack. So moving on to, before jumping into our sandwich attacks, we have to discuss something about automated market makers as well. So what are really these automated market makers in DeFi? Now, unlike traditional finances, where the price of an asset is decided by buyers and sellers trading that asset, this is called an order book method or order book approach. But in AMMs, or automated market makers, like Uniswap, they work on a constant product algorithm. So for example, Uniswap works on X multiplied by Y equals to K curve, where X and Y denotes the token reserves respectively, and K denotes the constant product. And the trade happens on a liquidity pool in AMM instead of between buyers and sellers in order book approach. So here there's a liquidity pool, so anyone can sell tokens and buy tokens from the liquidity pool. So at Uniswap, there's a mathematical formula. So if you are trying to swap a token X for token Y, it will be calculated as a formula on your screen, like Y multiplied by 0.997 multiplied by dx over x plus 0.997 multiplied by dx. So what is dx here? Dx is the amount of token X that you are selling. So if you are selling token X, it will increase the amount of token X reserve. So the output amount of token Y can be calculated with this mathematical formula. So this is the curve, right? A bad drawing. So it's something like X multiplied by Y equal to K. So assume this was the initial value of Y and X token reserves. So for example, if I'm selling some value as dx of token X, for example this much, so now the output amount, or what I'll be getting, is something right here, right? So this will be the dy. So this much amount I'll be getting from here, from this trade selling. So similarly, if I'm selling some Y token, it will increase the token Y reserve, for example here, and what I'll be getting is dx here, this much amount of dx. So as you can see, the curve flattens as we go ahead both on the x and y axis, meaning the less the token reserve will be, the more expensive it will become to buy that asset. So for example, if supply of token Y goes less, then it will become very expensive to buy it, and we have to sell a lot of token X into the pool to purchase token Y. So this is what something adversaries utilize to make profit. Alright, another important factor is the slippage. So what is slippage? So as we know that the market stays in a continuous state of change, so the prices for assets move up and down. Now the execution price of trade also differs from the expected price. So this is called as slippage. Now slippage happens when traders have to settle for a different price than they initially requested because of a movement in price in the market. So this difference come because the market price was different at the time order enters the market and at the execution of a trade. So there are two types of slippage. First is positive and negative. So positive is when the actual executed price is lower than the expected price for a buy order. So by positive slippage, the trader gets a better rate for his trade than what it has initially expected, right? Then there is a negative one where the executed price is higher than the expected price. So here the trader gets a bad price for the trade. Now moving on to the slippage tolerance. Now how we can calculate the slippage, because there is no sweet point. There is advantage and disadvantage for setting it too high or setting it too low. So how much it depends on how much slippage tolerance is bearable for a trader, or how much movement in price I can live with. So Uniswap gives this option to us. By default, it is predefined in the UI. You can select the slippage which you are considering. So we can adjust that as well. So what it is a percentage value for the slippage that we are that we want to set for our trade. So that will be converted into a minimum amount which we are willing to accept for our trade. So if there is a huge price shift in the market and the output amount for a trade is less than the set slippage, the transaction will be reverted. So I can keep my tokens, but I'll have to pay the gas fees. So now the question is, how much tolerance should be set? Too high or too low, both of them have the advantage and disadvantages. So if we set the slippage too low, the trade won't be able to adjust with the market price, and although I can keep my tokens, but I will lose the transaction fee, or I have to pay the transaction fee. But if I set it too high, then it will open the door for front-running attacks like sandwich attacks, because I as a user am willing to accept less tokens for my trade. So what will happen? Attacker will front run my trade for that same asset which I am trying to buy, and thereby increases my price, increases the price of my transaction by making the asset more expensive to buy. And then the adversary will backrun my transaction by selling that asset at a higher rate and extracting profit from the slippage or from the market shift that it had made. So there's no sweet spot for the slippage tolerance. So that's what the reason it gives birth to sandwich attacks. Now let's just talk over to our main topic of sandwich attacks. So here you can see a nice visual representation covering what are sandwich attacks. So here you can see that victim sends a transaction as TV from the node. It gets broadcasted to the Ethereum network and gets stored into the mempool. As the blockchain is public and decentralized, the information is distributed to all the nodes and everyone can see that. Now, adversary has already set a spy node into the network, so it sees the transaction from the victim and it observed it and try to find out whether it is profitable to front run it or not. By profitable, I mean like it is profitable or is it having a high enough slippage. So if it, what it will do, it releases two transactions as TA1 and TA2 by adjusting the gas price according to the victim transaction so as to make it a sandwich, and submits to the network. So these transactions are broadcasted again and again stored into the mempool. Now the miner is typically ordering the transactions according to the higher gas prices. So what it does, or how it picks the transaction, it picks the TA1, the attacker's first transaction, then the victim's transaction, and then the attacker's second transaction, thus making it a sandwich. And that's how sandwich attack looks like. Moving on to different variants of this sandwich attack. So sandwich attack can be performed by both the liquidity takers and liquidity providers. So these are two popular versions of sandwich attacks. So here you can see the first one is a liquidity taker attacking the taker. So here you can see the attacker sees a pending transaction from TV, a trade of X tokens for Y tokens. So adversary observed this pending transaction and try to find out whether it is profitable to make it a sandwich out of it or not. Once it find out that yes, it is profitable, and then it releases 2 transactions with appropriate gas fees in order to be picked up according to the descending gas fees, inserting victim transaction so as to make the sandwich. So the first transaction, DA1 from adversary, will be the transaction trading the same asset as victim, transact X for Y, which you can see. So because adversary knows the victim transaction is trading a large amount of an asset, which will be increasing the price of the token eventually. So adversary does the same trade prior to it, hereby increasing the price of the asset which the victim trying to buy. And as the victim transaction has a high slippage set, it will result the victim into a worse trade, as now its transaction is running on a modified price by the adversary, and the adversary state has made token Y more expensive to buy by buying it beforehand, before the victim transaction. So the victim transaction will result into a least amount possible, and afterwards it will backrun the victim transaction by selling the Y token at a higher price with transaction A2, TA2. So what it's doing is selling the Y tokens for X to get his X tokens back, and hereby earning profit in X tokens. So which will be more than what it initially had, and that all will come from the victim's trade. Moving on, there's another variant called performed by liquidity provider. So sandwich attack can be made by providers as well. So again, the motive is same for front running and back running a victim transaction. So how it's done here? So again, adversary sees transaction and observe the profitability out of it. The liquidity provider releases 3 transactions here. Firstly, the adversary front runs the victim transaction with TA1 by removing the liquidity. So what will happen? It will increase the unexpected slippage for the victim. And then at in transaction TA2, it restores back the liquidity by adding the liquidity into the pool by back running the victim transaction. And then finally, it transacts Y again to get his tokens, to get X tokens, to make its X tokens equal to what it had prior to the attack. So again, a very simple trick to make a sandwich out of victim's transaction and earn profit. So now we know that what sandwich attacks are and how are they executed. Now let's just talk about how we can prevent them. So let's just take a quick intro to zero knowledge proofs. We'll try to understand these zero knowledge proofs in a very simple example, with a very simple example. So actually, what are zero knowledge proofs? So you can take them as like a way to tell someone that you know something without actually sharing any information about that thing. Yeah. So let's take a very popular example to understand it. Considering there are 2 users, user A and user B. User A wants to sell 2 balls to user B, but the condition is he wants to reveal the balls to only that person who will actually buy that balls, and doesn't want to share any information about them to any other buyer, because a buyer can cancel a trade in between, but will also get the info about the balls. So on the other hand, the user B wants to buy 2 balls, but the condition is she wants them to be of different color. So here in the scenario, what user A will try, it will try to sell the 2 balls without sharing any information about them, but still making user B believe that they are actually of different color. So he will put a blindfold on her eyes and give the balls to her, Now user B wants to verify whether they are actually of different color or not, or user A just bluffing or lying about it. So what she does, she put the balls one in each hand, put her hands behind her back, and now she can decide whether to shuffle them or not. So if the balls are actually of different color, then user A will be in a position to find out whether she has shuffled her hands or not. So let's assume this first time user A correctly find out whether she has shuffled the balls or not, or shuffled her hands or not. But there is a chance that user A just bluffing or just making a wild guess out of it. Because yes, it is possible there are just two balls and the probability of making a wild guess here is just 1 by 2 or half of it. So but user for the first time user A correctly finds out that whether user B has shuffled the balls or not. But user B is not satisfied yet because as I just told user A can make a wild guess out of it. So what she does, she repeats the process one more time. Now the probability of making a wild guess for user A will be 1 by 4. So user B can repeat this process as many times as she wants until she gets satisfied, because we know that after n number of times the probability of guessing or making a wild guess will become so small that it will become almost impossible to make a wild guess for user A. Now user B has verified after a certain number of attempts that what user A is saying is right, and he can't make wild guesses these many times, and hence the balls are actually of different color. And now she can buy the balls and trade will be successful. So this way user A has sold the balls without even sharing any information about them. So this is a very simple example of zero knowledge proofs. So zero knowledge proofs are of two types, interactive and non-interactive. So the one example you are seeing, which I have just given, is an interactive one, where the prover user A and verify user B both are interacting with each other. There's also non-interactive proofs where a prover says the proof and the verifier can verify itself. So moving on to the next slide, there are three important parameters for zero knowledge proofs, or mandatory parameters for zero knowledge proofs to satisfy. The first is completeness, where if a statement is true, then the verifier will be convinced that prover possesses the correct input. Second is the soundness. So here, if a statement is false, then no dishonest prover can convince verifier that they have the correct input. Thirdly, the zero knowledge parameter. So if a statement is true, then no verifier learns anything other than the fact that the statement is true, which we have just seen. The user B, while making the trade, just had an idea that whatever user A is saying is true without getting any other information about those balls. So this is what zero knowledge proofs are. Now I will ask my partner, Mr. Gokul Alex, to share more about zero knowledge proofs, ZK snarks, and how we can use recurrent and recursive proofs to prevent these sandwich attacks. Over to you, sir.
Thank you, Tejaswa, for setting the context of the sandwich attack, the front-running attacks, and how the problem is becoming a big challenge for the decentralized finance protocols on Ethereum and other ledger systems. Now we are going to deep dive into the system of zero knowledge proofs and understand how we can address or try to address the problem of front running and back running and the sandwich attacks through zero knowledge systems. This paradigm of zero knowledge proofs were invented by three brilliant researchers in MIT, Massachusetts Institute of Technology, Professor Silvio Micali, Shafi Goldwasser, and Rakoff. And all the three, they came together with a groundbreaking conceptualization about probabilistic proof systems, which was in infancy till 1980s. So when we look at the history of zero knowledge proofs, 1985 is the time when this concept was proposed. It was written in a it seems it was published in a scientific journal like Scientific American. And by 1992, we could see that the research on zero knowledge proofs have grown, has risen exponentially. And we got something known as succinct zero knowledge proofs or space efficient zero knowledge proofs. And earlier, there were two paradigms of zero knowledge proofs. The initial architectures were about interactive proof systems. But in the interactive proof systems are not feasible in all the situations. And thus, a non-interactive system, argument system has its own merit when we look at a distributed system setting. That's when that so initially non-interactive proofs came into emergence, and then by 1992 succinct zero knowledge proofs came into existence. Ever since 1992, we have seen a lot of research into the various ways in which we can realize non-interactive zero knowledge proofs. And Pinocchio, which was invented or which was conceptualized in 2013, it's a milestone. It's a breakthrough, real breakthrough, because this has first time in the history of probabilistic proof systems made non-interactive proof systems really practically possible. Like Pinocchio was something that we can realize. And in 2016, Growth 16 based pairing, the Growth 16 is all about pairing based cryptographic system, elliptical curve based non-interactive zero knowledge proof system. And it really opened up the way for introducing the zero knowledge proofs into blockchain platform, and that has been the dawn of zero knowledge proof cryptography in blockchain systems. And then the size of the proofs and the need for trusted setup, these were two constraints in all the zero knowledge proof systems, and that's the challenge which is addressed by ZK Starks in 2018 by Professor Ben Elisasson and his team. Now, when we look at the zero knowledge proof system closely, how is it a radical change from the status quo? It can be seen as a transition from client-server architecture to prover-verifier architecture. Hence, we can say that this is more of an objective ontology for World Wide Web and Internet, because client-server architecture is something at the root of it. It's a service-oriented architecture, looking at web as a collection of services. But web has gone beyond just services. Web is now web connecting systems of meaning, systems of engagement, systems of truth, systems of trust. And hence we need something more than a client-server system. And that's where the prover-verifier paradigm becomes very, very prominent and relevant. Before we deep dive into zero knowledge proof systems further, we should understand that these are not the only privacy preserving paradigm or privacy technology that is being used in blockchain systems. Since we are talking about block village, presenting proof systems in block village, our focus would be on what are the ways in which these recursive and recurrent proof systems revolutionize or have the potential to revolutionize the privacy preserving paradigms. Along with ZK Snarks. ZK Snarks is the zero knowledge proof system used in Zcash and many other protocols. Along with it, we have protocols, other privacy technologies like CoinJoin, ring signatures, and Mimblewimble. You can see which all projects have implemented these privacy preserving technology. CoinJoin being used first time in Dash, ring signature, another milestone, another revolutionary privacy preserving technology that is used in Monero, and Mimblewimble used in Grin and Beam. When we say privacy preserving technology, there are two major priorities or the purpose for using privacy preserving technology, either to hide amount or hide the addresses. When we look at the zero knowledge proof system, now we need to understand zero knowledge proof systems in a little bit more closely. And now when we try to do that, we can see that zero knowledge proof systems work through initial trusted setup. That is, if I tell you broadly, zero knowledge proof systems can be classified into systems which require trusted setup. We call it a ceremony, or the zero knowledge proof system which doesn't require trusted setup. And there is another classification. What is it, a contextual snark or universal snark? Snark stands for succinct, non-interactive arguments of knowledge. As you see in this diagram, when you look at the life cycle, initially we set the parameters for the ceremony and the trusted setup. Then we do the key generation, there where we have some residue, toxic, it's called as toxic waste, and which has to be removed. And after that, there will be a common reference string, which is produced by the witness, and then there is an arithmetic circuit. So there we should understand that there is a transformation of proof from an argument of knowledge into an arithmetic circuit that happens in ZK Snark system. This is very important. Any arbitrary program, any argument of knowledge could be converted to an arithmetic circuit. This is the kind of transpilation, a transformative compilation that happens, which helps us to digitize the arguments of knowledge. That is what makes it very relevant in a blockchain-like system or any other digital decentralized distributed ledger. While we look at zero knowledge proof, as at the data level, there is subtle difference between the zero knowledge proofs and the UTXOs in Bitcoin. In the UTXO, it's something about the input that you give and the output that you generate. And the output of the previous transaction becomes the input of the next transaction. Whereas there is an aggregation of inputs. What you see is inputs are transformed to output, and then you generate a proof. So the proof is an intermediary step. Then this proof connects adjacent transactions. This is the very simplistic explanation of the difference between UTXO-based ledgers like Bitcoin and others and zero knowledge proof systems. When you look at the construction of a snark, what is very important is this. Here we are seeing the succinct non-interactive arguments of knowledge, snark, being used for a circuit SAT. SAT is a kind of NP-hard problem which is used for proving the difficulty of a lot of algorithms. So this is a circuit SAT problem. So you have to convert a circuit into a quadratic arithmetic program. This is the codification happening. So this kind of a NP-hard problem can be solved using the binary SAT problems. There are different kinds of SAT problems. These binary SAT problems can be solved using the construction of a snark. And the snark, here we deal with a snark where there is a common reference string. You can see that the SAT stands for satisfiability, right? So a binary circuit is codified into a expression, a mathematical expression. This is known as a quadratic arithmetic program expression. And that is the one powerful possibility from zero knowledge proof. So any circuit, any kind of circuit system, arithmetic circuit can be converted into an expression, a cryptographic expression, an NP-hard problem. This is a more detailed view of such a circuit. So on the left side, you are seeing a circuit system where we have different points of multiplication and addition in a circuit. And we are seeing how we are converting this circuit into a kind of logical expression. So this is where we can say that zero knowledge proof systems initially they convert an arbitrary program into arithmetic circuit, and from arithmetic circuits, it becomes a probabilistic proof, a probabilistic logic, a logical proof expression. What are the components of ZK snark? See, what you see in the previous slide is eventually when you depict it in a matrix representation, it is known as rank 1 constraint system, R1 systems. That is a specific kind of matrix representation. So we have initially an arithmetic arbitrary program is converted to an arithmetic circuit, and from there we generate R1 CS, rank 1 constraint systems. And from this rank 1 constraint systems, we can produce quadratic arithmetic programs, and we can produce linear proofs. So initially there is a computation at the hardware level where you could use FPGAs, ASICs, or any kind of GPUs for this computation. From the computation, you're producing an algebraic circuit, which is converted into a rank 1 constraint system, which gets transformed to a quadratic arithmetic program, which gets converted into a linear probabilistically checkable proof that is called PCP. This linearity is very important because we look at every replicated state machine in blockchain as a linear state machine. If it is a non-linear state machine, like a chaotic cryptographic system, then it would be a different paradigm altogether. So the use of R1 CS and quadratic arithmetic program is very important. And we should get linear probabilistic checkable proofs and linear interactive proofs, which eventually becomes the zero knowledge succinct non-interactive arguments of knowledge. So finally, the initial part is done by the prover and the witness. And finally, we have the verifier. The verifier verify whether it's a ZK snark. This is about ZK snark systems. So let's now reflect on this life cycle of ZK snarks. It transforms arguments of knowledge into arithmetic circuits, and it's a transpilation of circuits into R1 CS and the quadratic arithmetic programs. This diagram on the right side shows it a little bit more in a very simple manner. When we have an expression, we need to prove. For example, we want to prove that the 2 is a even number, or we want to prove that 7 is a prime number. We have to convert that into an arithmetic circuit. From that, we are synthesizing a rank 1 constraint system, which gets using inverse FFT, inverse Fourier transform, which gets converted to quadratic arithmetic program, and then it is fed to the prover. Prover generate the proof and send it to the verifier. Verifier verifies it. The same quadratic program, when we have a trusted setup, we generate the parameters. The parameters, there are two keys, verifier key and the prover key. Both prover and verifier work with their respective keys. So this is completely an asynchronous computing, computation. That's the power of it. It gives great security in an asynchronous setting, which is very, very strong requirement for various distributed systems like digital identity systems, various voting systems, or various kind of financial and non-financial use cases. Now, we have to think about how ZK snarks and generally zero knowledge proofs are relevant to cryptocurrencies. First, we start with expression, an argument of knowledge. Like we want to prove, whether we want to check the legality of a transaction. For example, we want to verify if this escrow contract is legal. First, we have to flatten the escrow logic or the escrow expression into a circuit that gets converted into a rank one constraint system, and then through inverse Fourier transform, it gets converted to a quadratic arithmetic program, and then it we send it to the prover. First, prover creates a transaction, off-chain transaction. Prover is an infinitely powerful Turing machine, and the verifier is a finite Turing machine with limited power, because verifiers most of the times in the cryptocurrency settings, verifier would be a smart contract or a particular system running on a replicated state machine in a blockchain. So that was a good introduction. That was just an introduction to the zero knowledge proofs. Now we have to see the larger spectrum. This has been a Cambrian explosion of zero knowledge proof. If I use the words of Professor Elie Ben Sazon, right? So there are different kind of snark compilers, pre-processing snarks, where we pre-process some of the proofs, and then there is a dark compiler, then there is a normal snark compiler. Snark compiler could be linear proof or linear encoding. Then we use different kind of fields and groups for creating commitments. The commitments can be different kind of commitments. It can be polynomial commitments of different type, such as Pedersen commitment, or recently there is a new commitment which is being introduced in Ethereum, and the proofs can be algebraic. So algebraic proofs are used in pre-processing snarks. Linear proofs are also used, and in systems like Stark, cryptographic hash functions and random polynomials have a lot of importance. There are three types of groups we can use: groups of unknown order, generic groups, and bilinear groups. Bilinear groups are commonly used in linear encoding systems, and groups of unknown order are used mainly with dark compiler. So we can also classify proof systems into the proof systems which use common reference string and the proof systems which use structured reference string. So common referencing is the simple implementation, and right now there are a lot of innovations coming up. Like we measure the performance of the systems based on the proof size and the verification time. So there are a lot of them, as you see in this diagram. Prominent CRS-based systems are Halo, Bulletproof, Fractal, and Aurora. Recently, new things are coming up like Spartan, Supersonic, which are very fast. The slower ones are like Bulletproof systems, Aurora, Ligero, etc. Aurora Lite has been introduced with a structured reference string. And the elliptical curve that we use, that's also a differentiator. Growth 16 has been one of the most popular one. and BTCV and MNT are also some other elliptical curves being used. Okay, now let's proceed to the next slide. Before moving, I just moved a little faster. So the next slide, what we need to, in this particular presentation, our focus is on recursive and recurrent proofs, how they are very useful for addressing sandwich attacks in DeFi systems. This is our proposal. Recursive logic has been implemented, or recursive proofs have been implemented in lot of systems, zero knowledge proof systems. Like Halo. Halo is one of the most popular examples of recursive proofs. We will deep dive, we'll see the recursive proof systems in a little bit detail here. And then we have we would like to propose two other set of logics based on incrementally verifiable computation, which is a white paper. Which is another white paper published by an MIT researcher. So we would like to propose identity logic in space and time, along with the inductive and iterative logic of recursive proofs. Moving on to the next slide. This diagram. So I just want to show you briefly what is an example of a recursive proof. Recursive proofs, early recursive proof systems were constructed using trusted setups and cycles of expensive pairing-friendly curves. This is an example of a recursive proof. And if you look at an example of a recursive proof construction, this shows how do we generate one proof which becomes the input to the another proof system, and how do we do recursion. So these two are based on MNT4 curve. One is based on MNT4 curve, other one is based on MNT6. These are two different kind of elliptical curve systems used in Mina protocol, which was earlier known as Coda protocol. Here we can see the example of recursion. So elements of a recursive proof system are the mainly incrementally verifiable computation is at the heart of recursive proof systems. So this is at the heart. We can use them the use cases are to verify the sequence of order of transactions. The one core concept of recursive proof systems is proof carrying data, which can be extended to obtain verifiable distributed computation. Halo is a very popular example for a recursive proof system, which has been proposed for various voting systems. Voting can be considered as a recursive proof activity because you do the same operations in a hierarchy, in a recursive way. You vote across for example, you do the same voting across countries. In countries, they do voting in different states continue that in districts or smaller local governance units. So Halo and Halo 2 are two proof systems with lot of recursive features. Now let's move to the next slide. Yeah, so now we are just trying to understand the Halo proof system. Halo proof system consists of a polynomial commitment scheme, which we mentioned earlier, and it uses inner product as the arguments are based on the inner product systems. We know outer product and inner product in sets, groups, and rings. Here it's based on inner product arguments, and it is a polynomial commitment scheme. It also uses a cycle of elliptical curve. Here it's an important point. The cycle of elliptical curve with proofs constructed on one curve that verify the proof constructed over the other. This relationship is very, very important for recursion, and which is very, very useful for reflexive proofs and recurrent proofs. This makes our proposition a real possibility. Recurrent proof system. Recurrent proof system, we are highlighting the importance of time, the dimensions of time and space together, because that is the only way we can prevent attacks from the attacks like the front running attack and the back running attack. Time transitivity of proof carrying data will be a metric, and then time is truncated because proofs have ability to compress the data. The time transitivity and time truncation capability of PCD, proof carrying data, is harnessed here. And then in the so the time variable, time becomes a dynamic variable here. That any changes in the time, the linear metric of time will be considered as a time turbulence. So we are introducing a time turbulence verification between the different actors in the mempool. That is what we are proposing in recurrent proof systems. And recurrent proof systems will be composable. So we want to use it in a multi-party computation setting. And then it will be made portable through interoperability between the proof system. That's the long-term roadmap. Initial roadmap is to achieve time transitivity in proof carrying data, and then time truncation and time turbulence verification. This will become clear to you when you see the solution architecture. So we want to give little bit details about time truncated proof systems. As we have mentioned about probabilistically checkable proofs, PCP. PCP is a very vast area in cryptography. PCP theorem is something everyone should refer if they are working on zero knowledge proof systems. PCP systems enable proofs to be verified in time polylogarithmic in length of a classical proof. This is why PCP theorem is at the heart of zero knowledge proof systems. The main equivalence is proof of knowledge is equivalent to time space complexity. This equivalence is leveraged or harnessed in building time truncated proof systems. So you know from earlier introduction by Tejaswai, you know that computation, the soundness, completeness, and the zero knowledge property, these are three properties. So soundness is very important. Computational soundness is very important for probabilistically checkable proofs, and that helps to shorten the length of the transmitted proof. So transmission of proof is very important for we have to understand the proofs are transmitted between different actors in a probabilistic proof system. That is the benefit we are leveraging to create time truncated proof systems. Moving on to the next slide. Yeah, so let me show the next slide. The recurrent proofs are the proof systems where prover uses space polynomial in the space of classical prover and time. So recurrent proofs will be a kind of metamorphosis between the space variables and time variables. That's why the prover becomes the time in which prover act on the proof is used to generate a time sensitive space polynomial. And it is the assumption is that this polynomial will be a linear polynomial, and when verifier verifies it, it will be a constant. That's how we are able to achieve it in a we don't get into a NP hard situation because the verifier verification happens in a constant time. So we would like to leverage the Spartan proof system for this recurrent proof construction. Moving on to the next slide. Let us show you the solution summary. Solution summary. The main thing is, as you have seen, the crux or the fulcrum of the attack on the sandwich attack happens on the mempool. So the access control to the mempool will be through proof of order and proof of hierarchical access. Because we are using recursive recurrent proof, we will be able to generate proof of order of transactions and proof of hierarchical access. Because in the near future, Ethereum is going into use incremental different Merkle trees called Verkle tree that will be launched in the near future by the Ethereum engineering. So our prover will be time optimal transaction prover using Spartan proof system, and we will leverage the recursive proof system of Halo 2. The proof carrying data at the will be used for storing the contract execution order on ZK Snark, and transaction ordering will be done through a new cryptographic library that we will create called triangular time locks. Triangular time lock will be a new constraint system which will be built using the ZK Stark of Starkware. So this we are trying to propose a system, a hybrid of ZK Snark and ZK Stark, where there will be triangular time locks. We will detail the anatomy of triangular time locks in our roadmap while we are working on it. Currently, we are working on triangular time locks. We have extensively worked on verifiable random functions and verifiable delay functions. So, but this time, this is a triangular time lock will be a time lock which is dynamically created at a particular space, time, trust instance. So this will be very useful for sharded distributed ledgers which are sharded. So triangular time locks we are introducing for sharded systems. Initially, we will come up with a smart contract based deployment, and later we will apply this into our proof system. So this is one of the first system with hybrid hierarchy of ZK Snark for access control and ZK Stark for the transaction ordering. So recursion, for recursion, we are leveraging ZK Snark, and for time locking, we use the ZK Stark because that's more faster, even though the proof size is bigger. But when you look at it, time is a timestamp or any time property in a distributed ledger is not big in size. So that's why we are confidently using ZK Stark system, and Starkware ZK Stark has been the best performing Stark system in the recent times. So the second one is, this will be the first integration between the VDF triangular time locks, VDF and ZK Starks. The ZK Stark already they have an integration in Starkware, but this will be one of the first hybrid hierarchy of ZK Snark and ZK Stark, and this will be one of the first system where the VDF will be integrated with the triangular time lock. And let me quickly take you to the diagram, the architecture diagram of our proposal. So this diagram shows you how we are going to leverage recursive proof and recurrent proofs. On one side we are doing transaction ordering. Second side we are doing transaction timing. This helps us to create a very versatile prover, which can make sure that the transaction that is coming from the real node, not from a spy node or an adversarial node, and then it can be verified by a verifier. So this is where all our changes are happening in the provers, not in the verifier side. Hence, we are expecting that this will be an interoperable system for multiple kind of ZK Snark and ZK Stark. But this is our early research. We have a lot more to work on this area. and we are really happy to get this opportunity to present this in DevCon. And thank you so much for giving this opportunity to DevCon 29 Block Village. And thank you all for listening to us. We will share the presentation with more details with the Block Village team.